Hello. So we learned what a derivative is in section 3.1. And now we're going to go a little further. See, in that first section, what we learned was the derivative at a single point. Okay, but instead of finding the derivative or the rate of change at every single point, and you have to take the limit of the difference quotient every single time at every single point, there is a much better way to do that, which is to take the derivative of at any point x. And so that's going to lead us to the derivative as a function, not at a single point. So that's what section 2 is about. So let's now get into section 3.2, derivative as a function. Okay, so now what we are going to do is to generalize the idea of the derivative, not as a single point, at a single point, but as a function, all right? So we are going to derive a new function based on the old function f. I'm going to go right into the definition of this derivative as a function because it's not too difficult to understand given what you have already learned. If f is a function, the derivative of f as a function is, okay, I'm going to use the same notation, f prime, because it's derived from the original function f. It's going to be the limit as h approaches 0, sounds familiar, right? But we are no longer going to be looking for the slope of the tangent line at a specific point. So instead of having a, we're just going to call this random point x, right? So f of x plus h minus f of x all over h, right? If it exists, because sometimes it may not. All right, and that's it. So this is the definition of the derivative as a function. Most times when we say that find the derivative, we are looking for the function which is derived from the original function. Okay, so I should also say this finding the derivative f prime. Okay, this we use a specific verb, which is actually a fairly common verb we use. Finding the derivative in mathematics is called the act of differentiation, differentiation, okay? And the calculus that has to do with the derivative is called the differential calculus, which is one of the two branches. Remember differential and integral calculus? And so if you are asked to differentiate a function, we don't mean like, oh yeah, this is different from this and this is different from that, okay? Differentiating a function means finding the derivative of the function, which is to find this limit, okay? All right, so remember f prime of x, what does it represent? It is the slope of the tangent line, now not at a specific point, but at any x. So if you can find this derivative as a function, then you can do that first, and then you can plug in these different numbers. What is the slope of, what's the rate of change at 5, 7, 20, and you can just plug in the number because you have this new function, which represents the slope of the tangent line at any point. It's also, of course, the instantaneous rate of change, instantaneous rate of change. Okay, so we're going to do a few things. I think let's say we did x squared. Well, like we can try it. All right, let's go ahead and differentiate several functions. Okay, maybe 4 or 5 of these. Right. So first, let's say let's try to find the derivative of 3x. Okay, you can probably find the answer. I mean, you can probably guess the answer to this. What is the slope of the tangent line at any point for the line 3x? The key word is line, right? It's a straight line. The slope is not going to change at any point. So the answer should be the constant function 3. Okay, well, let's figure this out. What do? We take the limit as h approaches 0 of 3. Well, let's go ahead and use the definition first. We don't have to write this every single time, but because this is the first time we are looking for the derivative as a function, let's go ahead and start with the definition. All right, in this specific case, f of x is 3 times x, so we just multiply this input, which is x plus h, by 3, and then minus, that's going to be 3x all over h. All right, that's simple enough. Remember, I'm writing this not in the shorthand notation I introduced to you before. So I am writing LIM. I will not do this all the time. The first time through, I should be a little more formal. So that's what I'm doing. 3x plus 3h minus 3x. Notice here. What do you notice? What do you notice? 3x and minus 3x disappear. And more than that, h and h cancel. So this just becomes the limit. Let me go ahead and write down that thing, 3h over h cancels. So that limit of the constant is 3 as expected. So at any x, the slope of 3x is, not surprisingly, 3 constant, okay? All right, let's go to the next one, x squared. What is the derivative? All right, so this time I'm going to use the shorthand notation without all the LIM as h approaches 0, okay? So what we need to find out is the limit of the difference quotient. So this is what I will have to write. You don't actually have to write down this first difference quotient if you know what that is. Because it's a square function, it's x plus h squared minus x squared over h. It's not too difficult, right? I mean, you may have thought when you learned this first, wow, this is really a huge fraction. Okay? In fact, I had, years ago, I had this one student who couldn't remember the definition of the derivative, and he just said, oh, it's that big fraction, and limit of this big fraction. Okay, well, that's good, but it's really not that big if you are getting used to mathematics. All right, how do you square a binomial? It's going to be, the first one squared plus 2 times the first times the second plus the second squared. In other words, this is the square of x plus h. And of course, you subtract x squared. Notice here, many times you subtract exactly what the first term is. All right, so 2x plus h, I am factoring out h from this and this, right? Because we have a strong motivation to do so, and that's to cancel h. All right, so this actually becomes 2x plus h. And of course, you are taking the limit as h approaches 0. And at this point, I will not use the equal sign. As h approaches 0, this expression just becomes 2x. And so that is the answer to the question, differentiate f x is equal to x squared. So the square function has its derivative 2x. Interesting, right? All right, number 3. This is actually giving us a sort of foreshadowing of what is to come. In the next few days, if I ask you to differentiate x to the 17th, you will be able to do so right away without doing any of this work, okay? All right, but let's do the third power, okay? How do you differentiate this? Now for this, I am going to give you a little prerequisite quiz, okay? Because at this point, you notice here, I had to square a polynomial, right? A binomial. This time it's going to require cubing of binomial. So do you remember what this is? You have to use, what is known as the binomial theorem. That's the one with a Pascal's triangle like this. So these numbers are going to be the coefficients for this. All right, so this will be a cubed plus 3a squared b plus 3ab squared plus b cubed. okay, if you remember that. And so, even if you don't remember it, it's still true, okay? Because that is the third line of the binomial theorem. And then if it's the fourth, the next line would look like 1, 4, 6, 4, 1, and so on. I trust you have seen Pascal's triangle. So what is that? Well, here, let's try to calculate this again. I will start with a difference quotient. And so x plus h has to be cubed minus x cubed over h. All right, so this is where I'm going to use this binomial theorem. X cubed plus 3x squared h plus 3xh squared plus h cubed, that's this part. And then minus x cubed all over h. Not surprisingly, the first and the last terms cancel each other. Everything else on the top, as you can see, has h. So let's factor out h. 3x squared plus 3x h. You have two of these, so once you take one away, you only have one left. Here I have 3 h's. I will take away one or factor out one, leaving us with 2 h's in the parentheses. These can be canceled. So what is the expression? 3x squared plus 3xh plus h squared. That, of course, is not the derivative because we are to take the limit as h approaches 0. This will go away and this will go away, leaving us with the derivative of 3x squared. All right, so notice here, this has become the coefficient and the number, the exponent has gone down by 1, which is going to be the general idea for taking the derivative. That was the third. Yeah, okay. Let's do something little different. This time, my function is going to be the square root of x, or x to the 1/2. All right, let's find the derivative, i.e., let's differentiate the function. So I am going to find the difference quotient. All right, so this is going to be, should I still write this? Yeah, I think it's a good starting point, to write this. All right, so what is the square root of x plus h? You can't really do much about it. You just have to write the radical of x plus h, and then minus square root of x. Okay, so we have a new problem here. What is the new problem? Well, there's nothing much we can do, right? Is there anything I can do here? I can't cancel anything. I am, this was nice before we could multiply things out. But what we can do is, when we have to take the limit, what the one thing we did when you have radical minus the radical? Well, yeah, the conjugate. So let's multiply this by the conjugate. See, at this point, you really don't have an idea if it's going to work. Okay? There's no guarantee. So you just try what may work. And if it doesn't work, you just start all over with a new idea. And this is really, and I should emphasize this is really what mathematicians do. Trying to solve a new problem and you get stuck and you just find some solution. This conjugate process may work, may not work. We just have to do it. And if you get stuck, you try something new. And when somebody comes up with a very creative way to solve a problem, then that becomes a new theorem or something, right? Okay, so once you multiply this out, the top is going to be x plus h. Remember, it's a minus b, a plus b. So it's going to be this squared minus this squared. X plus h minus x. That's nice, okay? Now, unfortunately, the denominator gets quite messy. But that's okay, right? Remember, I said it's all right. Your high school teacher may have told you not to have radical signs or irrational numbers in the denominator. You should always rationalize the denominator. What we have just done is to irrationalize the denominator, exactly the opposite. But see, sometimes it works because I think you can see now x and minus x can cancel, leaving you with h on the top, and h is already factored on the bottom. And oh, that's great, isn't it? Oh, I'm sorry, this is supposed to be the plus. Right? And so this is what you have. H and h will cancel. This will become 1 over the square root of x plus h plus the square root of x. Now, as h approaches 0, of course, this goes away, and this just becomes 1 over the square root of h plus the square root of x plus the square root of x. And so this is 1 over 2 square root of x. Or you can write this as 1/2 x to the negative 1/2 power. And so that is the derivative of the square root function. Notice here, x can't be 0 or the negative, any negative number. And negative numbers are already excluded from here. But 0 is actually, let's think about this, interesting, huh? What's happening with this radical or the square root function? Square root function looks like this, okay? And according to this, for instance, when x is equal to 1, the slope is 1/2. You see that? When you plug in 1 here, you get 1/2. So the slope of this tangent line is 1/2 right here, and so on. But as x gets closer and closer to 0, x can't be 0. X is defined at 0, but it can't be 0. So that means the derivative does not exist at 0. And in fact, as x approaches 0, closer and closer, you have to approach it from the right-hand side because there is no left-hand side here, right? As you approach 0 from the right, guess what happens to this expression? Stop and think, okay? If x is 0.00001 or something, this number, the denominator will get really small, but the numerator continues to be 1. So that number blows up to infinity, right? The derivative actually goes to positive infinity. And so that means when you're really, really close to 0, the slope is going to get bigger and bigger until it becomes vertical, completely vertical at 0, if the function is has the slope or the derivative is defined at 0, but it is not. So the derivative is actually not defined at 0, even though the point exists in the original function. Okay, so and we can keep doing this for other functions, but at this point we will go on to the next idea. The notation we use, so we used this to take the derivative or to describe the derivative as a function. All right, we could also write this weird expression dy over dx. I will explain this in a moment. You could also write this because the derivative is it has so many applications. Sometimes we use f prime, which probably is your preferred way of writing this. And the prime is something that indicates something that has come from the original function, right? So f prime is derived from the original function f, and that's why we use prime. Dy dx, this expression has its own usefulness and meaning, which I will explain in just a second. You could also write this as d dx of y or d dx of f. Okay, I'll explain this in a moment as well. So here's the picture. Let me draw a picture here. All right, so I have a slightly more complicated picture than before. This is some, point x, the independent variable. And so here's a point on the graph of f. All right, and so this point is f of x, of course. Right, now this is x plus h, and this is f of x plus h as before. All right, now what we have here is the real change between fx and f of x plus h is this, right? So that real change is called delta y. So this is the real difference in y as you go from x to x plus h, all right? And so that's, again, abbreviated delta y. So this is called delta x, the difference in the x values, which of course is h. Okay. Now we are also going to call this dy, dx. So d stands for infinitesimally small change. Okay. So and I'll explain this a little further in just a moment. And so this is the slope, or this is the tangent line, right? Okay, and the tangent line, if x or if h is really, really small, okay, then the tangent line is going to be really, really close to f. Now, this picture doesn't show that. I mean, this picture, the real difference is way up here. And if you follow the tangent line, it's this height difference, which is very different from delta y. But the idea is when h is really, really small, this difference in following the tangent line is going to approximate the real difference. And so this approximation is called delta y. All right, now you notice here, this line, let's call this line L, right? This tangent line L has a slope. Slope of L is, of course, the derivative at x, right? But if you look at this, that slope can be found as rise, that's a rise, over the run. And so that's dy over dx. And this is where this notation comes from. Dx and delta x are the same. D and delta indicate the same thing for the independent variable. But for the dependent variable, dy is the approximation for delta y. So dy approximates, this is called the linear approximation, which we'll be studying later, approximates delta y. If you don't quite understand this, like, this is too much information, that's okay. You don't have to completely understand this yet, because it is a rather difficult thing to remember. The differentiation part is what you should be focusing on. But I am saying this because, eventually it'll come to you, and the textbook also has this in section 2. Okay, so dy is going to be approximating, not yet, we will be doing this. Dy will approximate delta y, okay? And another thing, dy can be written. Now, this is not quite a ratio or not a fraction. Dy over dx is actually just another notation for the derivative function. But if you consider dy to be this length and dx to be this length here, you could spread this apart and pretend like this is a fraction. So you could also write dy is equal to f prime x times dx. And this is called the differential of the function, differential. And we will be using this for our linear approximation because dy is what we will be using. Okay. For right now, don't worry too much about this picture here, but that explains the notation dy dx. You probably don't like this very much at this point. Most people don't. I didn't like this for several years after finishing Calculus 1. So, but eventually, okay, you will be using this quite a bit, especially when you go into classes like differential equations. Even in Calculus 3, you will be using this quite a bit. All right, now notice here, d dx is sort of written separately here. And that's because, see, when you start with y, okay, you start with y, and see d dx is almost like saying, look, this is like a command saying, look, I want you to take y and differentiate it. I want you to take y and find the derivative for it. So d dx is called differential operator, which is like somebody telling you, hey, take the derivative, differentiate this. And this is the same thing, all right? D dx means differentiate what comes after that. And so as a differential operator, d dx can be preceded by what you are about to differentiate. So that explains these two last symbols for the derivative function, right? You'll be using probably this most, but don't be surprised when you start to see dy dx or y, well, y prime is easy, but any of these would still mean the same thing. And so just be aware of that. Okay, that's all I have for section 2. And well, actually, that's not true. I am going to stop this for right now before we go into the part 2 of section 2, where we do a little more theoretical things. Remember, I said the derivative sometimes may not exist. So when can you differentiate functions? What kind of functions do not have derivatives? And so I need to discuss that before we finish section 2. So that will be in the second part of this video. Okay,